Okay, may as well get started. Welcome everyone to the Grand Challenge session on Poynting Flux. The first speaker is going to be Brian Anderson of APL.
And Alex, what's my time limit you want me to go to? I've just forgotten, that's all.
15 minutes.
I think it's like 15 minutes? Or...
plus 3 for questions. Yeah.
Anyway, I'll start. All right, so that's the title. And I'm going to try to set the stage for people after me who are going to dig into this a lot deeper and just to make you aware of sort of where they're starting from and the challenges that we are confronting and prospects and progress that is being made. So if you cannot hear me, go ahead and unmute and let me know, but I hope that this is working out okay. All right, so starting off with some basic relations. So what do we mean by energy flux or Poynting flux? That fundamentally is from Poynting's theorem, which is E cross delta B, where the delta B is the variation from the background field primarily due to field line currents. And then the E is the convection electric field. That is the E cross B, the plasma velocity. The divergence of the Poynting flux, the negative of that divergence corresponds to the J dot E dissipation inside at a given point in space. If you integrate over volume, then the integral of E dot J over a volume is the same as the surface integral of the Poynting flux into that volume. And in the ionosphere, the way this works, if the ionosphere is this block that I've drawn here, where this is the top, you have an electric field in that direction and a magnetic perturbation in this direction, and then E cross delta B is a Poynting flux down into the volume. Now, for the work that what everybody, I think, assumes is that the Poynting flux out the sides is 0, and the Poynting flux out the bottom is 0, so that the integral of this Poynting flux over the top corresponds to the volume integral of the joule or the energy dissipation E dot J that's occurring inside that volume somewhere in there. So that's the very basics. Now let's talk about something else that's kind of basic, is that it seems simple enough, but the problem is that making sure that you've got the sign right for delta B can sometimes be tricky, especially near the convection reversal boundary. Same thing for the electric field. And you can tell that if you, for instance, have the wrong sign on your delta B, that it's actually over here when it should be over here, but your measurement is over here, you can see you get the wrong sign for S. Same thing if the electric field should be over here, but your measurement is actually this way, you get the wrong sign for S. And that's one of the basic reasons for erroneous upward Poynting flux. Not that the Poynting flux can never be upward, but that's one of the reasons for getting a lot of erroneous upward Poynting flux, is that these quantities E and delta B are not always the easiest things to measure. And sometimes if there's an uncertainty, it can lead to those kinds of things. We'll come back to that a little bit later on. So that's the gist of the Poynting flux, but the other thing that you want to be aware of is some basic relations for the current and the electric field. And the ionospheric current is described, the current density is described in terms of the Pedersen conductivity here is written as a function of altitude times the electric field, and the Hall conductivity as the B cross E, B hat cross E in a sense, or that's R hat is the way it's often written. In any case, this is at right angles to that. And then you can do the integral, the height integral of that to get the height integrated current density in the electric field and the Pedersen conductivities there. These are the height integrated conductivities. Now, the thing to bear in mind is that the Pedersen current, which is sigma p times E, sigma p the scalar, that has both a curl-free part and a divergence-free part. And you might be surprised that it has a divergence-free part. But where that comes from is if there are gradients in the Pedersen conductivity. Similarly, for the Hall current, that has a curl-free part. It might surprise you a little bit. And so, or it has a divergence, it has a curl-free part. And the reason for that is because of your gradients in the Hall conductivity. I'm not going to have to deal with that anymore in this presentation. Key thing is, though, that even given the gradients in the conductivity, E dot J, which is sigma p E squared, is always positive definite. Even if the neutral winds are driving the electric field, the dissipation is still positive definite in the ionosphere, that E dot J, in the Earth frame. And then sometimes that's written as the volume integral of E dot J over the volume, sometimes written as Q sub E for the for the dissipation that's in the volume. That's not the same thing as the Poynting flux, and we'll get to that in a second. All right, well, I know that's not true. The basic relations we want to talk about now are the neutral winds. And in the neutral wind frame, you have to get into the neutral wind frame to work out the energetics in terms of where the energy goes that's being dissipated in your volume that you've calculated with the Poynting flux. And if your neutral wind velocity is capital U, that is in the Earth frame, then you have to calculate this E prime, which is the electric field in the frame of the neutrals. And what you have to do is to take the electric field in the Earth frame and then add in the minus U cross B motional electric field in the neutral wind frame if you go into the neutral wind frame. So that the neutral wind frame electric field is E prime plus E is equal to E plus U cross B. Now, what you can do to find out where the energy goes, you can take this J dot E, but then to this E, inside that, you add and subtract U cross B, okay? And then when you add it, you get this term, and when you subtract it, you get this term. The term on the left is the actual heating in the neutral wind frame. So that's the actual heating of the neutral gas, or the joule dissipation. And you can see that it is only equal to J dot E when the neutral wind velocity is 0, which it almost never is. And the other term is you can arrange, and it's very convenient. That turns out to be the neutral wind velocity times the J cross B force. So that is the neutral wind acceleration. And so the partitioning between the energy is between the actual joule dissipation and then the mechanical energization of the neutral wind. Notice that by acceleration, you mean, of course, either acceleration or deceleration. It's just a net force on the neutral wind. So if you look at the partitioning of the energy from the electromagnetic energy, some of it goes in the joule heating and some of it goes in the mechanical energy in the neutral frame. And you have to do that in the neutral frame. So it's often written this way, where QE sub m is the joule heating plus the mechanical. The joule heating is given by this expression here, sigma PE plus the neutral wind velocity, or you can height integrate that. The important thing to notice in this relationship for QJ is that you can replace this E with the minus V cross B, and then you realize that this term in here is actually the difference in the neutral wind and the plasma velocity. So the QJ is actually proportional to the square of that vector difference. And then you can see that this really is a frictional heating term, what that is. Now, as far as the mechanical energy dissipation, you just integrate that over the height integral for the volume, and you notice that this Q sub m is not necessarily positive. The wind can either be speeding up or slowing down, depending on just what the sign of this dot product is. Okay. But there's an inconsistency problem that one has to confront. And to think that through, suppose that you have an electric field from one data set or a model, and then from a different data set or a model, you have your magnetic field perturbations. Now that could be that you have two different data sets, or you have two different models, or one of them is data and one of them is a model. In any case, consider if the expansion of the oval is slightly different between your representation for the electric field and your representation for the magnetic field perturbations. Or suppose that one pattern is shifted either sunward or duskward or somewhere, so that the convection reversal boundaries are displaced. That's the key thing. If those distributions for E and delta B are not if they are electrodynamically inconsistent, that is, if the convection reversal boundary is displaced between them, there can be regions with erroneous Poynting flux, either upward or downward. But that's a real problem. If you have an inconsistency between the electric and the magnetic fields, that can lead to fairly large regions where you're getting an erroneous Poynting flux. So one has to be careful about that. That actually motivated folks to take what I call the ionospheric electrodynamics view, where you integrate the convection electric field, the horizontal currents, use ground magnetometers as much as you can. This goes back to KRM back in the 80s. And that's related to the Birkeland currents this way. You can take these 4 expressions and then derive 2 expressions where the ground magnetometer equivalent currents are one source term, the field line currents are another. The potential, electric potential here, which is the electric field, and the horizontal currents given by the gradients in the equivalent currents and the electric field and the conductivities. You get 2 equations and 5 unknowns, and this is what you try to solve. And there's been a sort of a pretty consistent effort in the community over 3 decades, almost going on 3.5 now, to do that. And to try to understand the energy partitioning between storms. And this is just an example of an event that was looked at by Rosenquist back almost 14 years ago. And what they looked at was for a given storm, and they did some assimilated mapping of ionospheric electrodynamics, that's AMY, estimates for the Joule heating in that storm, using also empirical estimates using the upstream solar wind monitors and some indices to try to estimate what the total energy into the system and how it went to the different parts of the system. And what you see here is the total energy in divided by 10. So this is actually way up here somewhere. And this is the Joule heating estimate that they came up with from AMY. This is a Joule heating estimate from a couple of different empirical models based on AL. And you can see that the AMY estimate is substantially different from that up to an order of magnitude. So that tells you that we have a lot of room for improvement at that time. And their estimates for the particle heating, which were again just AL estimates, which probably were not very realistic, are there. But it looks like the Joule heating is dominating in this case. If you integrate all of that, then this is what you get in terms of the Joule heating versus the other estimates. So the AMY estimate is actually quite a bit larger. And it's larger than the estimates for the ring current at that time. So those are the example of estimates that were done. Problem is, we know that AMY had at that time had a long way to go. This is an example from Wilder where they used ground magnetometers, DMSP, electric fields, and SuperDARN, and then derived what the Joule heating was for this particular time during the April 5th, 2010 interval. And then what they did is then they added in the estimates for the field line currents with actually the magnetic perturbations from the Iridium constellation as served by Ampere. And the distribution for the Joule heating changed dramatically. That doesn't necessarily tell you that this version on the right is correct. It just tells you that there's a lot of uncertainty, and it really matters what data sets you're using for this assimilation. Just to drive that point home, they also looked at the peak Joule heating rate at a given time anywhere over the hemisphere, and then what the integrated was. And you can see that there are factors of 4 or larger difference. Sometimes one is larger. Generally, the one using more data tends to be larger. But the typical Joule heating rates totally for the storm, they get up to a couple hundred. In this case, if you believe this estimate, up over 500 gigawatts during the storm. So there's a lot of, this gives you some idea of the uncertainty that we're confronting in trying to get these estimates. But it's worse than that because we're actually doing a lot of smoothing with these data. And this is work that Matsuo and Richmond did about 12 years ago. There are things that are resolved in our models. There are observations that are unresolved. And then there are things that are subgrid that we can't resolve in the models that we use. And they actually looked at that and decomposed it in a number of different ways. And the story is right here. This is the Weimer model and the smooth curve. This is an actual DE observation of the electric field. This is the residuals relative to the model. They're quite large. These are the residuals that are subscale in the simulation they could do, in the modeling they would do, and this is what was resolved. And you can see that the resolved residuals capture pretty much what's going on here. This is the residuals. This is what was actually, this is the variance in those things. And you can see that the residuals are actually really, really large relative to the signals that we're seeing. So we really miss a lot in some of the models where we have the smoothing. And so we have to pay a lot of attention to that. This just shows if you're using the model, this is what you're actually resolving, what you're getting. If you actually resolve what we can get in the observations that's within the grids of the simulations they were doing, you're actually doing a pretty good job. And then if you add the unresolved things, there's yet another factor of maybe 50%, sometimes maybe a factor of 2, depending on how large the background is, for what the uncertainties are. So sometimes the small stuff matters, and certainly the stuff that's not, that we have to be very careful about what resolution we're using to try to resolve these things. And then, of course, there are neutral winds. They're really important, but they're really hard to measure. I'm going to go through this fairly quickly so as to keep us on time. This is work that Deng and Ridley did, again, about 13 years ago. They used some GITM runs with a hypothetical just BZ turned southward, and they ran it, and then they just averaged things over this interval just to get a feel for what happens. And they use electric fields from Weimer and then auroral power that way from the particles. And then what you see is this is the Q sub E, whereas this is Q sub J. And it's clear that they are not very close to each other. So the neutral winds are playing a big role in determining how this system is behaving. This is a busy plot, but this shows Q sub E along with the plasma velocities. And this is the neutral wind velocities. And you can see there are large regions where those velocities are perpendicular to each other. And in some places where they're almost anti-parallel, like right in here. Well, those are going to be the regions where the frictional heating, which is the real Q sub J, is the largest, which is right over here. If you were to just take Q sub E, you would think it would be largest here and here, but it's actually not. The Joule heating is really the largest over there. Now, with some ISCAT results that were obtained back in 2012, I'm going to go through this pretty quickly. This is relatively not very disturbed, more disturbed, and very disturbed. Basically, what you see is that the actual Joule heating and the mechanical dissipation are actually comparable for moderate levels of activity. What we would measure, which is the electromagnetic energy flux, is this little line down here. So we're not really getting a very good picture of what's actually happening in the system with respect to the Joule heating and the electromagnetic. This is where the neutral winds are driving things mostly. But as things get more and more strongly driven, then the Poynting flux, or the Q sub E that we measure, starts to look like the Joule heating. But even so, the neutral winds play a very important role. I'm going to skip this slide in the interest of time. We have done some more work. Gong Lu has done some really good work and continues to do good work on assimilating storms, where we take everything that we have, put it into the circulation models, and then try to reproduce what satellites are measuring for neutral densities. This is observed at the satellite altitude, simulated with those inputs at the satellite altitude, and this is at a constant altitude. And here you can really see the traveling atmospheric disturbances that show up. But this agreement is reasonably good. Now that's part of where we need to improve. So what are the prospects for what we should do? Ionospheric electrodynamic specification is really hard, but it's getting better. And it's really important that the electric fields and the magnetic fields that we use are evaluated self-consistency, so that we get a better handle on QE sub M. But there's a lot more we have to do, even with that. So, and it centers on the neutral winds, I think, because the neutral winds govern their partitioning between Q sub J and the mechanical energy. They can lead to upward Poynting flux, in part due to the neutral dynamo. And they play a very important role in determining where the Joule heating actually maximizes. And hence, they play a really important role on the density enhancements high in the thermosphere. The other thing is that for prospects, the dynamics of the high latitude driving, the inertia in the neutral winds, and then thermospheric circulation physics, they all couple together. And there are time delays and spatial displacements that come into the system that you have to factor in. And the coupled electrodynamics driven by observations can be used to drive your thermospheric simulations, circulation simulations. So those have to be tested then by whatever wind and density observations you have. That may be a very promising avenue for research because it folds in all this coupling. I think one big area that we need to work on is to be quantitative about what we mean by agreement. Because you can get agreement with a simulation like this, but that doesn't necessarily mean that it is the only answer and it's uniquely correct. And one way to get a better handle on that is by being quantitative about what we mean by agreement. And I hope that's a good jump start to the rest of the talks in this session. Thank you.
Thanks a lot, Brian. That was a great start. I wonder, there's one question in the chat. Uh, can you explain a little more about electromagnetically inconsistent delta E and delta B?
Yeah, sure. I don't know that I'm going to go to a different slide to talk about that. What I mean is that if you have, say, a model for, say, the convection electric field, and then perhaps you have observations for, say, the field line currents or the delta Bs, the conditions for which you've got those observations probably don't match what you're representing with the model. There may be field line currents where, for instance, you don't have any large electric field in your model. That's what I mean by inconsistencies, that electrodynamically they're not consistent.
Okay. Well, with that, I'm gonna maybe ask you to stop sharing the screen and see if Dolores Knipp can share her screen for the next talk.
I'm coming in to share my screen. Just one moment. Is that showing?
No? Yeah, I see it fine. So please, please feel free to start.
Thank you. Thank you, Brian, for the great introduction. It'll save me a bit of time. So I'm going to jump into one of the possibilities for measuring a Poynting flux from satellites, spacecraft. We've had constellations of spacecraft flying for many years now that can make along orbit measurements only, but if we consolidate these measurements, it gives us a pretty good and to some degree surprising view of what is going on with Poynting flux. So Liam Kilcommons, who has, that's the we, and mostly that's Liam, has been working on Poynting flux and extracting it for 6 satellite years of DMSP. We took a year in solar cycle 23 and 2 years in solar cycle 24 that we've put together. He has a series of automated algorithms, several of which have been described in documents that I'll mention, that help us to prepare and filter the data. In this presentation, we're using only the highest quality, that's quality flag 1 ion drift data. I'll mention a little bit about that and then get to the results that we have from this consolidated effort in terms of how much Poynting flux is coming into the polar cap versus the auroral zones, and then a 1-slide summary on what challenges we continue to face. So as Brian mentioned, the divergence of the Poynting vector quantifies the energy that is coming into and out of the atmosphere. Our interest is the energy coming into the atmosphere, with several assumptions that can be considered to be a local measure of energy input. We are actually looking at comparing our Poynting flux to consistently estimated simple joule heating. I don't think I have time to go over that today, but I'd be glad to discuss that via Slack. As Jeff Thayer and Josh Simider pointed out long ago, this Poynting flux is a huge source of the energy for neutral heating. It does move the mass in the thermosphere around. So these are 2 strong reasons for looking at this energy input, especially when it's when we need to think about it in terms of expanded atmosphere for satellite drag. So my emphasis here is going to be on the instruments that measure the relevant input, the electric fields and the magnetic perturbations. We'll be looking at only a long field component of the Poynting flux, which is primarily downward, as Brian mentioned. The data from DMSP comes in at 1 second, so that gives you about an 8-kilometer spatial resolution. Behind all of these efforts are significant work in improving the spacecraft location so that we know exactly where the DMSP are. You may not realize it, but a lot of the information, early information in databases, is a forecast location for spacecraft, which is usually right, but we found a few times when spacecraft were elsewhere in the universe. Liam Kilcommons has been really dedicated in removing spikes and jumps and trends in the magnetic field data. And we have also removed some contamination in the particles. Now you may say, wait a minute, particles don't play a role in the Poynting flux. That's true, but I want to show you Poynting flux in terms of, is it in the auroral zone or in the polar cap or in the subauroral zone? And for that, we're using the particle measurements to put some auroral boundaries on in a dynamic sense. And then we are detrending the drift data. That is still work in progress, but you'll get to see some of it. So the data sets that we're using over here on the right, as I did mention, the precipitating particles are helping us locate the auroral boundary. That's information that is coming in to be applied not only to the DMSP magnetometer data, but also to the electric field data. So the slight colorings that you see here in yellow and purple are indicating when we are in, respectively, the yellow is polar cap and the purple is our best estimate of when the measurements are being made in the auroral zone. And you can see that with just a diagram here of the particle spectra so that you can kind of see how we're doing that. Bringing that forward just a little bit more, we have an automated auroral boundary identification that was introduced by Redmond, improved by Liam Kilcommons, and so we can get, as a satellite is going over one hemisphere or the other, the equatorward boundary of a pass coming into the auroral zone, the polar boundary, polar cap, and then polar boundary again, and equatorward boundary. This algorithm calculates a figure of merit to help us quantify the confidence in the identification of those boundaries. And you can read more about that in these two references. So here is an example of the magnetometer processing that Liam has published. We do have to remove some baseline variations, some of which are simply associated with the IGRF magnetic field. Some of that baseline is being contributed by a DST or a magnetospheric current that can influence that. We'd like to try and remove that kind of contamination. And when we do that with Liam's automated baseline removal, then we come up with the magnetic perturbations that we believe are associated with the field aligned currents, which are feeding into the Poynting flux calculation. And this is just a map up on top that shows you, if we do that over the course of a summer, what the field aligned currents look like. Region 1 here, poleward, and region 2, which are a little bit more diffuse. Equatorward, this is northern hemisphere and southern hemisphere. So now let's come into the DMSP ion drift. As I mentioned, this is work in progress. We have to combine information from the retarding potential analyzer, which gives us the X direction, and the ion drift meter, which gives us the Y direction for these for the drift velocity or the electric field, which is coming into this Poynting flux calculation. But you might notice here that there are some double lines, and there are also some cryptic comments up here. So these double lines here are indicating what we have done visually. It's been done quantitatively, but just to illustrate for you, adjustments that are being made on a daily basis, as I will explain momentarily, in order to come up with a baseline corrected RPA and ion drift meter. Let me see here. These cryptic comments here are where we're indicating the quality of the data. This is quality flag 1. So these only quality flag 1 data are what you will see in the subsequent results. But Liam managed to find here a pass that had something for every run in terms of quality flags. We're still trying to determine if we might be able to bring some of the quality flag 2 data in, but that is work in progress that we're doing with our colleagues at University of Texas at Dallas. Let's see. So what do? We're looking at each of these velocity components coming in from the drift on a daily basis, fitting a sinusoidal baseline using ridge regression to all of the quality 1 data that are available for a spacecraft a day. We've tried seasonal, we've tried yearly, we've tried by spacecraft, and it turns out that at this point, we're still having to make these daily corrections. We subtract that model to get a baseline corrected velocity, and that is what is going into our Poynting flux calculations. So here's an example of the Poynting flux calculation. It is now identified with the yellow regions being the polar cap Poynting flux and the purple regions being the Poynting flux that is associated with the auroral zones. And as I mentioned, subsequent results will show only information from the data that is quality flag 1, but just wanted to show you what it looked like when we see, as we're processing it, all of the different quality flags coming in. Here's a situation where right at the edge of the polar cap boundary going into an auroral zone, we have a pretty substantial input of Poynting flux down to about incoming 25 milliwatts per meter squared. That's a pretty high value. Most of the values are much closer to about 5 milliwatts per meter squared. And here's finally, we're getting to the results. If we put those 6 spacecraft years of data together using only the quality 1 flags, here's what we see in terms of Poynting flux. We're northern hemisphere on the left, southern hemisphere on the right. We're actually starting to see a pretty full view of what the Poynting flux looks like. Not surprising to us, but maybe surprising to some folks, is that climatologically, the Poynting flux that is entering the atmosphere is really on the day side, and it is strongly associated with the shear regions that come about when BY is dominant or when it's changing. So here is these results sorted now into IMF components BY negative and positive. You can see that the BY polarity on the Poynting flux shifts in this 9 to 11 magnetic local time frame, depending on what the sign of BY is. And now you can really see that this dayside Poynting flux is IMF BY dominated. And these values here, these are median values in each of these tiny bins. So this top value here as a median is 2.5 milliwatts per meter squared. If we now go through and sort these and only plot the data from those previous results that are exclusive to the auroral regions, we get a slightly different picture. We get less influence from 9 to 11. We get much more influence, especially in this region that I am speculating is associated with SAPS. So there's a strong dusk side flux near the equatorward edge of the auroral boundary. The IMF BY influence is much less. What is interesting to me is no matter whether we're looking at the full data set or the split data set, we're not seeing as much information or Poynting flux that's appearing in the southern hemisphere. That is true when we have the full data set. It's a little harder to say that that's absolutely the case in the split data set because now our statistics are getting a little bit thin. So some of the missing data here is only present because we've got everything combined up here. We're requiring at least 20 data points to fill a bin before we display it. So what is very interesting to me is this propensity for there to be Poynting flux at the equatorward boundary in the auroral zone. One reason that it may be absent here is there's a paper written back in 2012 by, I think it's Kumari et al., that identified some of the variations in the magnetic field in the southern hemisphere were starting to come under the influence of the South Atlantic, excuse me, anomaly region here, and we may have just enough variations that we do not get consistently strong Poynting flux there. But there, it may be there on a pass-by-pass basis. Going one more slide, I just want to show you if we now sort it rather than polar cap. Oops, did I skip over polar cap? Oh, no, there's the polar cap. So there's the polar cap. And again, if we're looking at only data that are in the polar cap, there is a lot of Poynting flux coming into the polar cap. But again, it seems to be strongly IMF-BY influenced. But it is the dominant on a climatological basis Poynting flux coming in, which probably explains why there's a lot of satellite neutral density, satellite measured neutral density perturbations in this region. So getting close to summing up here, we've taken one more cut, and that's looking at where is there really consistently large Poynting flux. Again, it is showing up in what we have identified as being the day side IMF-BY dominated. That does not mean that it's not present in the auroral zones. It is. It's just on a statistical basis, it's kind of overshining by the IMF-BY day side flux. So just a quick summary. We've gotten 6 spacecraft years of data from DMSP into shape that we are confident in actually showing it in a somewhat public presentation. We think there's funding coming down the pike that will allow us to process a lot more data. That's the good news. The bad news, there's always some limitations with the DMSP electric fields and ion drift measurements because of the contamination by light ions. But we're working with UTD to extract as much of that as we can, potentially maybe even using some of the medium quality data. We have been combining information from the sensor packages on these 3 spacecraft. These DMSP constellations are the only ones that I know of that have multi-year measurements from enough sensor packages that we can make this calculation. We've been able then, with especially the particle data, to figure out where the spacecraft are making these measurements in terms of auroral boundaries. Is the measurement in the polar cap or in the auroral region? We want to continue to improve our automated algorithms and filters to bring in more data. And just as a geophysical result, we show that there is a hot spot of Poynting flux in the polar cap that is strongly modulated by the IMF BY component, and that is the dominant Poynting flux over the long term. The northern hemisphere shows a strong Poynting flux during what I believe to be SAPS activation, but we've got a little bit more work to do on that. And with that, I will be happy to take questions or hold until question and answer period if that's more appropriate.
Thank you very much, Dolores. There are a couple of questions in the chat. Some of them have already been cleared up by Liam Kilcommons, but the lowest one seems to be, have you compared the Poynting flux in quiet time versus storm time? How much could the values differ? What's the maximum possible value of Poynting flux that you've ever observed?
Let me take the last question first. The maximum value that we have seen is 175 milliwatts per meter squared. That was on the day side in one of the extreme flow channels associated with a very large IMF BY. There have been some very large measurements also during storm time. I think I have seen once up to 100 milliwatts per meter squared in an auroral zone measurement. To go back and answer the first question, we have done some sorts of these data by KP. As you might imagine, if we're sticking with just the quality flag 1 data, the data get pretty thinned out during the higher levels of activity. So we haven't done that to the point that I'm comfortable presenting it, but it is very much on our to-do list. And as soon as we can get enough data that I think it's statistically viable, we will hopefully be presenting on that in short order.
Okay, thank you very much. There's one other short question, if there's just a minute. The hotspot of Poynting flux in the polar cap, is that associated with the cusp region?
I have been chided about saying whether or not that is cusp, because apparently, well, not apparently, it is true. Cusp has a particular definition. So I'm not going to use those words. There are people who certainly will. Yua Ding and her group at UTD, with whom I collaborate, have made it an effort to look at this and identified what is cusp, and I believe it's the boundary region just outside of the cusp. There is more stronger energy input into the cusp compared to just outside of the cusp. But we have, in this presentation, have avoided using those words and just using it as being associated with the flow channel associated with BY. And if you'll notice, these flow channel regions or polar cap flux areas extend well over into the dawn side beyond what would normally be considered cusp region.
Okay, well, thanks a lot for that, and I think now it's time to move on. So if you could stop the share, I believe.
Yes, I will do that. Stopping now.
Thank you. Leslie LaMarche, I think, is the next speaker.
Yes.
Okay.
Yes. Right, can everyone see the presentation?
Looks good to me.
Okay. So yes, I'm Leslie. I'm going to be talking today about observations of ion heating with the Resolute Bay incoherent scatter radars. And this is some work I've been working on with Roger Varney and Ashton Reimer. All of us are at SRI International. So just a quick introduction. Frictional and Joule heating, as we've seen before, is an important factor in energy deposition in the polar cap ionosphere. Heating can cause ion outflow, which contributes to coupling. The Resolute Bay Incoherent Scatter Radar, or RISER, is located, it's deep within the polar cap, it's 82 degrees MLAT. It's really in a very good location for observing Joule heating and ion outwards, polewards of the cusp. So what we've done in this study is we're examining ion heating events that have been observed by RISER in the polar cap. And then as a second part, we're going to look to see if these events can be explained by models driven by convection and precipitation models that cover the entire polar cap. So these ion heating events as we observe at RISER. RISER can measure the electron density and ion and electron temperature. So we're focusing on the ion temperature for this study. This is what you see for one particular event. Basically, you end up with this fairly substantial heating event or enhancement in ion temperature. This is near the noon sector. And up here, I also have the IMF-BZ component. And you can see that kind of coincident with this heating event, you have this large period of predominantly northward IMF-BZ. So the question we wanted to address to start is how often do we see things like this, heating events like this with at riser, and are they in fact correlated with northwards IMF-BZ? How we're going about that, or kind of the geometry I'm talking about here, is basically when you have northwards IMF-BZ, you end up with reconnection occurring in the lobe, which can drive four-cell or asymmetric convection patterns. So in addition to plasma moving from the sun side, day side to the night side, you'll sometimes have additional cells where you actually end up with sunward flows. So this is kind of in the middle of the event I was just showing. This is location of riser. You can see that it's actually really in the middle of this strong sunward convection flow as measured by SuperDARM. So how we're going about this, investigating if this is common, we're actually going to look at the entire riser database. So riser-N has been operational from 2019 until now. So we're actually included, the entire database from 2009 through 2019. Looking for long pulse. So these are F region experiments with a boresight beam. From those set of experiments, we extracted the median ion temperature between 200 to 400 kilometers. So basically we're looking at the kind of the center of the F region. We take that entire set of data and we want to bin it based on IMF clock angle and MLT, and then find the average median ion temperature in each bin. And when we do all that, we end up with this plot on the right. So IMF clock angle of 0 corresponds to northward IMs F. So this is the situation we were just talking about. And you can see that there's a distinct enhancement here representing that we do see on average a lot of higher temperatures corresponding to the conditions of IMF northward or low reconnection, and when riser is in the noon sector. So the next step we want to do here is we actually wanted to attempt to model this phenomena. We're using the ionosphere polar wind model, or IPWM. It's a 3D model of plasma dynamics and ion outflow in the polar cap. It solves an 8-moment transport equation for hydrogen, helium, and oxygen ions, and calculates photochemistry for 6 other species. It does this on a non-orthogonal magnetic dipole coordinate grid. We're using for this, it has variable grid spaces, but for this presentation, we're using approximately a 2-degree grid. Neutral parameters come from MSIS and EVU from HUBAC. Historically, IPWM has been driven by convection output from the MFLFM model. However, because we're actually going to try and model the results of a particular event we observed at a particular day, we want to drive it with data-based input from that day. So to do that, we're taking the precipitation pattern that we plug into IPWM from Ovation Prime. Ovation Prime is a model of discrete and diffuse auroral precipitation. It predicts total energy flux, total number flux, and average characteristic energy. It includes several different kinds of precipitation, which we do include in the IPWM model, and it's based on decades of DMSP particle energy data. So you can kind of see from these example plots here that it gives you, we can get from it the energy and number flux of precipitating particles in the auroral zone and at high latitudes. For convection, we actually tried 2 different approaches. The first is using SuperDARM convection maps. So SuperDARM is this network of high latitude HF ionospheric radars, and line of sight velocities from individual radars can be inverted into a full convection pattern in the polar cap. And this is an example, again, kind of from the middle of the event I showed earlier, where you have your 2 large convection cells, but then also some sunward convection, and that's kind of the center of where riser is. The fact that we have a lot of echoes here gives us a lot of confidence. So that means that SuperDARN actually observed data at that point, that this sunward flow is a real phenomenon that's occurring in the polar cap at that point in time. So one of the considerations you have to make with SuperDARN is that if there is not backscatter, so in regions where there's not, it's to use a statistical pattern based on previous SuperDARN measurements to kind of fill in an entire convection pattern. The other approach we used is the Ampere data set, which I believe was discussed with a lot of detail earlier. Again, magnetic field data from the Iridium satellites. If you assume a constant electric potential, constant conductivity, you can create these IPWM the same way we're using SuperDARN convection maps. One advantage to the Iridium approach or the Ampere approach is that because the Iridium satellites are in polar orbits, you get much more uniform longitudinal coverage. So I'm going to try right now to show you, hopefully everyone can see this. So this is an animation that's showing the SuperDARN results from driving with Ovation Prime and SuperDARN IPWM. So this cross is where riser is, and you see that you do have this heating event that we capture here, but also continue to have like a lot of heating in the cusp. And then this is the same, but with Ampere. And one thing you'll notice is that there are substantial differences between driving with Ampere and driving with SuperDARN. You do see a lot less of the heating in around the region where riser is, and where, although you do see a little bit of it, but we do still see some temperature enhancements in the cusp. So yeah, that's the SuperDARN results, and those are the Ampere results. So you can see there are differences between the two, and we think these are mostly driven by differences between the potential patterns from the two approaches. So now if we go back and actually compare both of these runs to the riser data, this is the same event I showed at the beginning of the talk, and this is this enhancement that occurs around the noon sector. You're actually seeing that in neither cases, IPWM really captures how significant this heating is. In the SuperDARN case, you do see an enhancement here that looks like it about aligns with the enhancement we see in IPWM, although the timing isn't quite right. And then for this first enhancement, there is some indication of structuring up here or temperature enhancements up here that might be similar. Ampere, there's a small enhancement in this region, which again is not really aligned with this, but it could be an attempt to, or something coming close. But really what we get from this is that both these kind of large scale convection maps, using them to drive IPWM, are not capturing the kind of heating that we're observing with the radar. So our conclusions here is that ion heating is something we observe with riser, and we observe it frequently, particularly in the noon sector under IMF-BZ northwards conditions. What we're thinking is that the sunward flow driven by low Greek connection are maybe associated with these heating events. However, we cannot reproduce this very well right now with modeling driven by global convection and precipitation patterns, which suggests that there is important work to do in the future to kind of capture what dynamics are not fully being captured right now by the model. And so these are things that I think were discussed in the introductory talk, but one option is small and mesoscale flows that may not be really captured with these large convection models are very important. Another one is neutral winds. So Roger Varney presented a talk at AGU where he showed that when you have neutral winds that are, or convection that may have reversed quickly from neutral winds. You can have substantial, that could cause a substantial enhancement in the heating that we observe, and that's not necessarily captured if you're not considering neutral winds correctly. And then finally, small scale precipitation features that also are not captured in the global models could modify the conductivity or conductance and cause additional factors that we aren't currently considering. So if there are any questions, I can take them now.
Yeah, great talk, Leslie. There's a question in the chat. Do you filter out weak IMF conditions, like IMF be less than a nanotesla, for example?
Oh, I assume you're talking about the statistical analysis. No, we did not. This is for
That's the
all
whole thing.
IMF conditions.
Okay, I actually have a question. Do you have any idea or suggestions how we could separate between I think you had 3 different potential causes of the failure of the observation, the large scale observations to match the riser data?
So right now, these are all just ideas that I think need to be investigated more in the future. All 3 of them could, and probably a combination of all 3, need to be properly accounted for to kind of get the model up to fully reproducing the heating we're observing. Yeah, the only way I know to try it is to kind of try all 3 of them individually and then combinations of them and see what is needed and what are important factors to bring things together. So in the riser data, for instance, you do see some features that indicate there is precipitation at scales smaller than what would probably be captured by the global model for this event.
Right. So maybe we need to refine those observations to do it to get this thing to work globally. There's a question also in the polar cap. What is the altitude dependence of an ion temperature enhancement caused by Joule heating?
Sorry. I'm not entirely sure how to answer this question. I know we do see. I know there is a difference between what happens in the E region and the F region. Let's see if I can actually, but there is. I know heating in the F region and heating in the E region can cause significantly different effects. So these kinds of considerations are important. But yeah, from the observational point of view, yeah, I might have to look at that one more.
Okay, well, thanks a lot for another great talk. And I think next up is, I believe, Tomoko Matsuo.
Hello.
Hello.
No. Okay, so can I share the screen? So let's see. Can you see my
Yes.
screen?
Yeah, looks good. Thank you.
Okay, so hello everyone. Great to connect virtually, and thank you very much for opportunity to speak, even though I am part of convener, so I guess get the time. So what I like to talk about is I want to give you updates on our exciting AskCube project, which is started last September, and it's a 3-year project. So we are just still beginning of our project. And then I am Tomoko Matsuo from CU Boulder, and then I'm PI, and I'm leading this AskCube project together with co-PIs Mike Ronomy from Virginia Tech, and Brian Anderson. You heard from him at the beginning, Brian Anderson from APL and Johns Hopkins. So what you're looking at is, by the way, iPoster. I made this iPoster for RSCube meeting, just ended, just happened last week. But looks like we are going to do this for AGU, and I thought it might be interesting to give presentation in this mode for this CEDAR. So I also posted a link to iPoster, which you can actually view at your own time later. And but I'm going to give you a tour of this iPoster as an introduction and an update to our RSCube project titled Assimilative Mapping of Geospace Observations, AMGEO, Data Science Tools for Collaborative Geospace System Science. So idea of AMGEO is basically to the essence, we try to make very sort of popular assimilative mapping procedure we have in community, AMI, which is built upon KRM that was developed both in 80s. And so AMI it's been used for high latitude electrodynamic study, including estimation of Joule heating and sometimes Poynting flux. And then, so we want to make basically what AMI can do, assimilative mapping, accessible to many people so that you can do it yourself, and then also you can expand. So with the focus is reproducibility of the results, right? And also accessibility. And we want to make this procedure as transparent as possible, meaning that everything is going to be open source. And then so that you can you can look at yourself and then make it expandable so that you can add your own module. So talking about accessibility, and so there's a number of ways to address accessibility. One of the hurdle that we try to sort of remove from users or potential future developers of AMGEO is that we want AMGEO software to talk directly directly with, let's say, SuperDAN data server, SuperMag, and exciting thing that's coming up as a version 2 is directly talk with Ampere database. Version 1, which was released last December, which also posted the website, amgeo.colorado.edu. And then you can actually, after registration, you can download yourself and you can start playing with it. And that version 1, actually, you don't need, it's Python, open source after registration. So you can actually grab all the source code from GitHub directly. So you don't need to leave Python session to grab data from SuperDAN and the SuperMag website. Okay, so in the previous speakers, you were looking at SuperDAN convection patterns, but hopefully with ease, you can create your own convection patterns that merges SuperDAN line of sight velocities with ground-based magnetometer data. And then soon, hopefully in December this year, you can actually merge Ampere just like using native mapping. There are additional features. We're going to use Ampere data in a different way than AMI does. Those are the improvements or changes that you will see in upcoming release. So this is very important because this part that we are told, and then including myself, by the way, I started as a graduate student of Kamide back in Japan. And then I was a PhD student of Richmond. So I myself went through that. So it's very much time consuming to clean up, standardize, and do all the pre-processing of all the data we feed into Amy. So we remove all the obstacles from future users and the developer of ArmGeo. So in this AskU project, you don't need to do all those processing. We're sharing all those tools as a package, as a part of ArmGeo package, or some of them are done in a data service that we provide at the CU. Okay, so that's very exciting. Things it's already there for SuperDAN and SuperMag. Version 1's been released, and then version 2 we're gonna add Ampere assimilative capability, and then we like to add more data, which I'm gonna talk about a bit later. Okay, so that's the purpose and then objectives and big picture. So let's go back to here. So this is the front page of assimilative mapping of geospace observations website. So I encourage you go there and then register, and then registration is required because we need to keep track of for NSF reporting purpose. We need to keep statistics. So, but otherwise, it's source code is available from GitHub. Okay, so what assimilative mapping does is in bottom line is that it's solving, if you are familiar with Kalman filter, it's solving Kalman filter measurements update equations. It's been shown here, or in other way that it's called in assimilation field is optimal interpolation, right? So, and then states that we are solving for is all different kinds of electrodynamics variables, electric field, which is electrostatic fields, and field lines, and then both Peterson and Hall currents. And we could actually, derived product is gonna be, quantity is gonna be Joule heating and Poynting flux as well. Important part is that just like in Amy, in ArmGeo, we make assumptions that all the electrodynamics state variables are linearly related, which you can do that if we assume that conductance is in known prior appropriate if conductance is known. So if you specify conductance, and we can actually relate all the variables. And then addition to that, we make a lot of assumptions about current geometries. So field line is vertical in here, and then also horizontal currents flows in a basically slab. Okay, so it's a very simplified current geometry. But with that, we can actually relate, we can borrow information from different observations. Version 1, out of box, you can assimilate SuperDAN and SuperMag, but we are gonna add the capability to assimilate space-based magnetometer data, Ampere irradium data, and then and also update to what difference from Amy's background model is different. So conductance is coming from Ovation Prime, as mentioned in the previous speakers. So Ovation Prime model is used as a background, and then also background model for SuperDAN or convection pattern is coming from Cousin and Shepherd. These gonna be updated in a version 2, and then all following release. And then so that's just these background models for the mean, and then covariance gives the constraints so that we can deal with the data gap. Okay, so this is what you're looking at here is that one figure from Cousin et al. In 2015. So this is what you're going to see. This capability is going to be added in a version 2. So what we did, what Ellen Cousin did in 2015 with myself and Richmond is that we ingested irradium magnetometer data processed by Ampere project in a very different way than Amy does. So I spare the details, but what you like to see, what, for this interest of this focus group is that, so you could see, so that the third column, this is the Poynting flux. And then the left is, you can see the electrostatic potential patterns and black contours, and the middle is a field line current. So Brian Anderson mentioned uncertainty, right? And then when you start actually bringing all the data sets together, we need to really we need to be very, very careful keeping track of uncertainty. So you can see that on top, let's see here. So there's a gap in irradium data here. So you could get that field line current, of course, just using irradium data. But where you don't have data, we can actually borrow information from CEDAR line of sight velocities data, right? So you could actually fill in this gap using very different observations. And you can see the uncertainty, which is the background orange contours, that you could see that the uncertainty is reduced by combining different sources of data. And then more interestingly, that here you go, this is the Poynting flux. The Poynting flux estimate only using one data set. So this is basically, you get the convection patterns using SuperDAN only, and then use let's say that we estimated magnetic perturbation, which using irradium data coming from Ampere project, and I could independently estimate those, and I could get the Poynting flux, you get this. And then we do here the bottom one, this is the bottom right. You do the merging inside the ArmGeo, and then you get the different Poynting flux estimations. Okay, so this is still large scale, and then as pointed out clearly from previous speaker, that this is not definitely, myself, I produce these maps, and then I do sometimes write the papers, right? And then it's very important that really interpretation of Poynting flux coming from large scale assimilative mapping procedure, you have to be very, very careful. And then please pay attention to uncertainty that we can estimate and then make it easy to use for your research. So okay, so that's what ArmGeo can help you to do science. Okay. And here you go. So this is just that sort of here in this section that you could play this later. That's movies are posted here, so you can see. So this is just a rendering of ArmGeo electrostatic potential for multiple CME events in early September 2017, and this was an interesting event. And then this was presented last year, the CEDAR Jam session. So we have a few frames listed here. And then what the ASCII project, as an ASCII project, we have a lot of collaborators on it. And then we like to look at this few events, focus events. And then we like to produce events we like to do in-depth of ArmGeo outputs, and then working with this grand challenge focus effort is really excellent. So far we are working with GEM conductance challenge efforts. They're looking at a few events and other thoughts on this. And so future plans. So as I mentioned, version 1 has been released, and it has capability to assimilate ground-based magnetometer served through SuperMag, and then also line of sight plasma drip measurements coming from SuperDAN. And December of this year, we are working very hard to make capability to direct AMSURE to directly to talk with Ampere data server. And also we have to update the procedures itself inside AMSURE. And then we are working also how uncertainty quantifications go into assimilated mapping. So there are different type of uncertainty. One type of uncertainty is coming from measurements, or how measurements being converted to usable form that we can assimilate. So we are very much tracking down uncertainty coming from both ends, coming from algorithm, coming from all the assumptions that we use, but also coming from data providers. And then they are part of ASCII projects. So hopefully we have a bit increased transparency in this data product. And then the following year, we are revamping how we do conductance mapping, and then start experimenting how we might be able to use, for example, SUSY images, and definitely DMSP SSJ particle data will be part of it. And then we're working hard on that too. And then excitingly, also we're working with this McDonald, and then how we can make use of very untraditional citizen science data for this scientific purpose. Okay, then finally, we are working with NASA CCMC, and then also SRI INZIO project, which is also funded by ASCII, led by Asti Bart at the SRI. So we try to make sure that AMSURE is interoperable with all the community data tools. Okay, and then finally, we like to produce with community engagement, useful reanalysis data products, and then hopefully be served by through NOAA and CEI. Okay, so that's not going to come in a few years, but that's our plans. And then thank you very much for your time, for your attention. And I'll take question from you.
Thank you very much, Tomoko. There's a question, how did you calculate the uncertainty? I also have a question, how you propagate the solution forward in time.
In time, so there are two questions. One is that, okay, so here you go. So uncertainty can be tracked through basically incorporation of uncertainty coming from two sources. One is, you can see that, denoted here, it's C sub B, which is covariance. And then, so that is a part of it. And then there's uncertainty, which you cannot see in these equations. So if you're familiar with Kalman measurements updates, the Kalman filter, so measurements update equations, so this is a so-called K is Kalman gain. Inside the Kalman gain, there are two sources of uncertainty could get into. And that is one coming from assumption of prior assumptions, and the other one coming from measurements. But then in the measurements error, there's two, actually we could break it down to two, but let's say more pure data error or uncertainty coming from measurements. And the other one is something called representativeness error. And that's where we could actually tap in, do better job about, how, for example, AMSURE is a functional analysis method. So that means that we are using spherical cap functions or basis functions. Basis functions resolutions really matters how we can represent the measurements, right? So that is called representativeness error. So we are actually quantifying those. So we are revamping those quantifications of representativeness error that could go into Kalman gain, and then also measurement error that is basically work of Brian and agronomy, and then their teams. They're really, we working together that we try to get a useful uncertainty from each data set. And then, my team is working on background term to get this prior era. And that is basically mapped down to, well, can propagate to analysis uncertainty. And then this was actually part of ANI itself, but then wasn't used that way or wasn't emphasized. And then, so that's gonna be part of AMSUR output. And so that's one question. Sorry, I get passionate about uncertainty. Time, oh yeah, so this is, at this point, it's snapshot analysis. And then I'm working with one of the undergraduate students that try to see that temporal propagation. So if you're familiar with common filter, we could actually do time update as well. And then we're working on that, incorporating time update as well. So then in a simple, way to say it, and then we could make the AMSUR procedure more traditional common filter as well. So that will come in the future.
Okay. Thank you very much. I think we have to move on to the next talk now from Bill Bristow. And Bill has given me his slides, but hopefully he can share it first.
I'm trying to, hang on. I just lost my view, so hang on here.
You have an X300 and some antennas on screen now.
That's actually the wrong file even. So let me stop the share, new share. But I don't have the view on my screen. Maybe, there, no, that's not it. Let me stop sharing, get out of that view, share screen. And, okay, can you see SuperDAR and high resolution potentials?
Yes. Yeah.
Okay. I still am not actually seeing it on my screen here, so I'm not quite sure how to do this. Maybe Alex, you could go ahead and show the slides, and I will stop sharing my screen. And go to the beginning.
Okay.
Okay, thanks. Next slide. Okay, hello everyone. So I've been working with Yue Deng and some others about using SuperDAR potentials to drive GITM in using the high resolution potentials. And I'm going to talk about in this talk just how we get them. And the purpose of what Yue is doing has been looking at getting Joule heating estimates. I think if you heard her talk yesterday, you saw what improvements you get when you look at things in high resolution. And then later you'll have another talk in this session by Sheng to look at the same topic. So with that, Alex, go ahead to the next slide. Okay, so this is what most of us are familiar with for SuperDAR and potential patterns. We've been using them for many years. This is based on the technique that Mike Hanami developed. I think it's a paper in '96 describing the technique. Basically, we use these quite a bit. You've seen some of them used here. So Alex, if you go to the next slide. So to understand how those patterns are produced, I think most people know this already, but just as background, we take all of the available line of sight measurements at a given time. So the figure on the left is for a 2-minute interval, all of the line of sight observations from all of the Northern Hemisphere radars shown there. And then we combine those with a statistical model. What I'm showing here is from the Thomas Shepard model. I think it's the most recent of the statistical models available. And then those are combined by a spherical harmonic expansion of the potential, and then using both the background model and the line of sight observations to constrain all these squares fit. And then so that's fit to give you the potential contours, and then superposed on that figure on the right are vectors for every location where we have a line of sight measurement. Those line of sight measurements are combined with the potentials to produce estimates of the vector velocities. So go ahead, next slide. So I compare what we have for our statistical model, the Thomas Shepard model, with the Weimer model. That's used quite broadly. It's produced in essentially the same way. The Weimer had 2,900 passes from DE2 spacecraft. So it was a 2-year mission back from 81 to 83, and took all of those and produced a spherical harmonic expansion of the potential, and used those line of sight, or I'm sorry, the drift velocities measured by the satellite to produce the potential contours. Our model is based on, I think this one on, I don't know, 15 years of line of sight SuperDARN observations combined in precisely the same way. So this is something that could also be used as a standalone model. And I think Evan has mentioned to me that it is going to be available on the CCMC soon for people to use as a driver for their simulations. Okay, next slide. Okay, so in the past couple of years, I've been showing figures like this, which is a different type of analysis to get not potentials, but to get vector velocities from the SuperDARN measurements. And it's a fundamentally different way. The line of sight velocities are used directly to calculate vector velocities without the intervening step of a functional expansion or potentials. It still requires some assumption and some regularization, but it is basically the main assumption is that locally that the divergence of the velocity field is zero. And with that, and then also using prior information that the global scale velocities are probably a decent estimate of the background convection. Combining those things, you can produce maps like this. If you go down, and next slide. So this is described. The algorithm is described in the paper that's on the previous slide. It's basically an application of inverse theory, geophysical inverse theory, to SuperDARN data. You find a model of that a line of sight velocity is the projection of a vector velocity along the radar look direction. A couple of other assumptions, and then just do a least square solution to this system of equations. Okay, go ahead to the next slide. Okay, and so the local vectors, I think Brian said something about you can analyze things differently, and you don't know that they're right. It's just different. But by comparing them with other observations, you can get a sense for if it is right. And this is something that's taken from that original paper on the algorithm. Just comparing the line of sight velocities, the vector velocities with observed auroral brightness, and you actually see a really good correspondence between what you observe in the flows and what you observe in the aurora. So it's some confidence that it's actually doing a pretty good job of reproducing the convection. Okay, next slide. So we've started to apply this in a couple of papers. So this is figures from a paper by former postdoc Andrew Keene, who was working with me in Alaska. This is using the local vector velocities combined with estimates of the precipitation from using ground-based imagers, and using that to produce estimates of Joule heating within the field of view of those imagers. And then we took the temperatures that you estimate from those Joule heating rates and compared them with measured ion temperatures from Pfizer, and got really pretty good agreement for it. And then to emphasize one of the points that was made earlier, that you need to worry about the neutral winds in addition to what's happening in the electric field. In the figure on the right, you see two sets of columns, and the first set of three is mapping the heating rates without taking into account the neutral winds. And then on the right set of three columns, that's heating rates when you're using the winds that you get from Mark Condi's Fabry-Pro imagers. And you really do get significantly different heating rates, and it's quite dynamic. You see things changing over pretty short time scales in those heating rates. So, okay, next slide. Okay, and I also want to advertise this. This is some other work that we've been doing to push things towards even higher resolution and mapping vector flows. We actually see features in the convection that are much smaller than you can certainly ever capture with one of the global models. In the figure on the right-hand side there, it's kind of subtle, but you can see a flow channel in the flows that are probably less than 100 kilometers wide, and it's also, again, very dynamic. You see this moving around. I don't know what this would contribute to a large scale Joule heating, but locally certainly it's going to be something pretty important. So, okay, next slide. Okay, so as I said, this technique gives you velocities, but it doesn't give you potentials. And if you want to use this to drive a simulation, most simulations don't ingest velocities directly. They need an electric field or potential so that they can calculate the velocity as a function of altitude. In the lower altitudes, of course, you've got it's collisional, and you end up with the field, or I'm sorry, the velocity not being E cross B. So it's straightforward, of course, to translate from an electric field to a potential. Assuming that the electric field is derived from a potential, so it's a static situation, then you can use this just simply that the potential at any point is the line integral from some other known point, integrating the electric field from a known potential to whatever point you have. And that is one way you could translate the velocity measurements into a potential. Problem is, it doesn't actually work well. I'd say that there are measurement errors, but there's also dynamics, and things are changing on really short timescales. And the assumption that goes into making that line integral path independent is that things don't change with time. So even though this is a 2-minute snapshot, or actually 1-minute snapshot of the convection, there's still time variations that different radars are seeing different parts of that area at slightly different times. And it's enough that, in whatever other source of errors there may be, it's enough to make it not quite perfect. You end up with, you go across the field of view in one direction and you would get to a value potential, and going from another direction, it's not going to match up exactly. So what I've done is, instead of solving it directly via the line integral, I write a system of equations over for every pixel within the area as that is the gradient, and that you got the derivative of the potential in the x direction is the electric field in the x direction at that point. Likewise in the y, and then you end up with a large system of equations. and just solve that as simultaneous equations over the full field of view. And with that, I'm getting pretty decent estimates of what the potential looks like. So if you hit down, pick down again. So there is that same interval looking at the potential there. And it looks pretty nice actually. And you see down in the lower region, you have a SAPS flow, and you get a nice gradient of the potential across that. It smooths out a bit, and you get into the auroral zone, and you get another gradient of the potential there coming up. Yeah, I guess not much to say about that. So go on to the next slide, please. Okay, so this is related, but not directly. So this is a time series of data showing 1 hour's worth of observations at a 3-second cadence. And the main reason I put this up here is a cautionary tale, in that if you look in the period, it's between 8:10 and 8:20. You see that large change in the line of sight velocities from being as much as 1,000 meters per second towards the radar to something like 250, 500 meters per second away from the radar in a very short time. And this is along a single beam, like I said, 3-second cadence observations. So you see, it's not noise; it is a true abrupt shift of the velocities. So down one slide, please. So if you look at the potential at the two, just before and just after that transition, I don't have control of the pointer, but if you look down in Alex, by the southern part of Alaska, maybe if you can figure out where that is, there's an area where in the bottom figure the flows are very much suppressed. So at that instant, in the western part of the field of view, the flows are still very substantial. In that region, just to the eastern part there of that, where that's suppressed, almost very low flows. So almost certainly there was a big dump precipitation at that time, putting the brakes on the flow, but it's not everywhere. And if you didn't have those high time cadence observations, you might just question what the potential is giving to you. Or what the flow vectors are giving to you. It is something that, it's always something you have to worry about when you're doing a numerical analysis of data. But you do see these features that are very short-lived or happen very quickly. And if you are using data that's over a longer period of time, you're going to violate assumptions about stationarity and get the wrong answers. So. Okay, let's go down one more slide. All right, so to be able to merge or to use the potentials to drive a global circulation model like GITM, you need to have potential specified everywhere. So the local divergence-free fitting technique provides you an estimate of the potential only in a localized region. It is very computationally intensive, and the larger your region, the computation just gets too big. So you can't do the entire high latitude region. So what we've done is to merge the standard Rahanomy type estimate of the potential over the full globe with the high resolution region, and so this figure is simply plotting one over the other, and there's a region where you can see the contours are slightly darker. The blues are darker, and the reds are darker. And we constrain the local potential on the boundaries so that it matches with the global potential. That is a boundary condition that's needed for just doing the solution in the first place. And then you can see inside where it's difficult really to see significant differences in this view, but they do line up pretty nicely. While it looks pretty nice, there are still a couple of issues in that right at the boundaries, you're transitioning from one type of solution to a different type of solution. So you can end up with an artificial electric field at that point. So to make it smoother, we had to do a little bit of cheating and actually merge them, not right at the boundary. It did a multiplied by a function to do the merging. So if you go down one slide. So at the boundary, we use this logistic function to blend the global with the local. So it is a smooth and gets rid of that abrupt transition between the two solutions. Okay, one more slide.